Yeah, that's me. Okay, let's see. So tomorrow I'm going to talk about, today I meant, I'm going to talk about graph sparsifiers. And subgraph sparsifiers. There is a chance that this might fall down. I'm just letting you know. So, what is a graph sparsifier? Let's give some motivation of the problem and what's have been done in the literature. So, say you're having a graph G here, which is pretty dense, and you're asked to find a graph G tilde that it's sparse. Say, with different weights on edges, possibly. I don't know, something like that. So that G and G bar are close in some meaningful notion of closeness. So the notion we'll be using is that if you look at the Laplacian of G and the quadratic form associated with it, then that's approximately the same as if you look at the quadratic form of the Laplacian of G tilde. And in fact, I mean, that's no rocket science. Right now, if that seems a little strange to you, then it's just a generalization of a very natural notion of sparsification, that if you look at a cut in graph G, yeah, so if you look at a cut S and S bar in graph G, a cut sparsifier of G tilde would be just a graph that approximates the weight that goes across each such cut. So this is just a generalization of the notion that asks for every cut, the total number of edges that go across the cut in G is about the same as the total number of edges that go across the cut in G tilde. And you know, if you want to interpret it in those terms and see the connection more easily, then if you look at a vector that's a 0, 1, characteristic vector of the cut and has 1 on one side, 0 on the other, this is just the quadratic form of the Laplacian, only restricted on those vectors. So that's just a stronger notion of cut sparsifiers. So those were mostly introduced by Benzer-Karger. And those were introduced by Spielmann-Teng and then studied Spielmann-Srivastava and Batson-Spielmann-Srivastava, who proved that every graph has a sparsifier with almost linear number of edges.
So when you use this notation, it's like an up to constant multiplicative factor or multiplicative factor close to 1.
So you 1 plus epsilon. So you have to. You want
This notation or this notation?
No, this is the tilde.
Okay, so it's 1 plus minus epsilon, but you could ask, any constant. You could ask anything you want. So it doesn't.
But when you state the theorem, what notion do you use?
I wanted to be more general because in what follows, I'm going to use approximation that is as bad as 1 over root n. It doesn't. It depends on the application. So maybe sometimes you ask the condition number to not be less than something. The standard notion that people use is 1 plus minus epsilon.
So generally, like you could say that there is a subscript of C or like a constant above it, like and it's up a C approximation.
So define. Give me two parameters, C1 and C2. Then I'm asked that this is greater than C1 times this, less than C2 times this. So like the standard notion is 1 plus minus epsilon, but for other applications you might want to relax things to get better edges or whatever you want to get, or maybe you can get 1 plus minus epsilon. So okay, but what has been done so far, just to give you an overview, is Spielmann-Teng introduced this spectral. Note that this also says that every eigenvalue in G.
I think too small. I think you should write bigger, and then it will be seen better both by us and the audience.
Okay, so that notion also but it just I put this thing here and it ruined my nice presentation. Okay, so this also implies that the spectrum is the same with the same approximation, which I haven't said yet what it is. That's just a consequence of that. Okay, so Spielman-Teg showed that in almost linear time, so in time m log n, or some log terms that I had in the tilde annotation, you can find sparsifiers with that many number of edges, and then over epsilon squared, roughly, but yeah, okay. But I haven't said epsilon here, that's why I'm not saying anything about that yet. So I mean, in fact, if you have different constants, that could be not depending on those. So anyway, yeah, in general, if you have this epsilon, guaranteed this is over epsilon squared. So Spielman-Srivastava improved that and found a randomized algorithm that with high probability finds an n order of n log n, okay, over epsilon squared if you want 1 plus minus epsilon edge sparsifier in almost linear time. And then recently, last year, Batson, Spielman, Srivastava, which Nikhil talked about it here, found the linear number of edge sparsifier, but at the time is, I don't know, something like as bad as m squared. So it's a deterministic algorithm, but it runs in really bad time. Okay, so that's what's been done, roughly.
Sorry to push you on the epsilon. I just wanted to know how small can the epsilon get?
For the probabilistic things, you can think of it as over 1 over log n. I mean, if it's any constant, so any small constant, so whatever, if it's 1 over log n, you would not have n log n edges anymore. You would have log n to the c. So it really depends on. If you wanted constant, could be any small constant.
So if I'm willing to add more edges, can I take it to the n to the minus 0.1?
Then you're going to have basically n times some function of n edges. So it's not a sparsifier.
So he's asking, suppose he wants polynomial error. 1 plus 1 over root 10, or 1
I'm pretty sure you can. I haven't really thought about it like that, but it's just I think you can.
Basically, that expression works for any epsilon.
Yeah. So I mean, in particular, if you want n squared edges, then it's trivial, right? You take the whole graph.
The talk by Nikhil, it seems that you can just achieve average degree d and have the spectral gap or all the bounds on the eigenvalues be 1 over root d, which is the optimum. Or root d, it's not normalized. Root d, like Ramanujan, maybe up to a factor of 2 for any d. This seems to work. So yeah, I think it was the whole n.
Okay, so that's graph sparsification, and now let's see what subgraph sparsification, which is what this is joint work with Makarychev, so it's me, Makarychev, Saberi, and Teng, and yeah, the dot is me. But, so we were trying to, so then the notion of subgraph sparsification anyway. So now you have two graphs. So your graph is a union of two graphs, G1 and G2, and you're asked to keep G1 fixed and sparsify G2. So find a G2 tilde such that G tilde equals G1 plus G2 tilde is a sparsifier of G. So one of the previous notions of sparsification. And you would ideally want to do that with optimal number of edges. So you wouldn't want to do it with order of n edges of G2 because this is trivial by techniques that's been used. So for example, if you had G1 to be the complete bipartite graph, plus 1 edge, say, and you had G2 to be, the star on this extra vertex. So G1 is here, and G2 is here. then you basically, it would be an overkill if you picked order of n edges out of G2 to approximate this thing, because already G1 is good enough in most directions. So, you would want to pick order of 1 edges of G2 and have the, with weights, of course, with different weights. So it would look like that, say, thick edges here. And have this G1 plus G2 tilde to be a good approximation of G1 plus G2. And that could be done, but it couldn't be done with these techniques. So that's a different notion of sparsification. So the plan of this talk will be, first I'm going to give some review, not overview, of what notions and definitions I need in order to go through the proofs of those things. And then I'm going to present, some parts of the proof of the BSS sparsification, which goes with potential functions. If you don't know what I'm talking about, you'll know in a bit. So that's 1, that's 2. And 3, I'm going to show how to do subgraph sparsification, which will involve restricting whatever proof I'm going to give here on subspaces. And then, as an application of that, I'm going to show how to make a graph into an expander, if a graph can be made into an expander with small number of edges. In general, optimizing algebraic connectivity of a graph by adding few edges. So that's the plan. So let's go to the first part, which just going to talk about graph Laplacians. The cut space of a graph and other notions of that form. So as you probably all know, but if you don't, stop me. I mean, I'm not going to give like a full background, of everything, but if you don't know, ask me. So for graph G, the Laplacian of a graph is just a matrix that's defined. Actually, I'm going to give 3 equivalent definitions. So one of them is the diagonal matrix with a degree of a node in the diagonal minus the adjacency matrix of a graph. That's the graph Laplacian. But also you could see it as follows. If you take any edge in the graph and pick an orientation arbitrarily for that edge, you define the incidence matrix, which is an m by n matrix. So say G has n nodes, m edges, and maybe weights, but maybe not. But now I'm going to take that weights are 0, 1. So either edge exists or not, just for simplicity. Could be weighted graph, doesn't matter. So this is the incidence matrix, and it's defined as 1 if V is head, minus 1 if it's the tail, and 0 otherwise. That's the incidence matrix of the graph. So you can have the graph Laplacian denoted as just B transpose B. If you had a weights on there, that would be a diagonal matrix with the weights here, but let's not worry about that right now. And Laplacian, it's a PSD matrix. And in fact, for connected graphs, only one eigenvalue is 0. So if you look at the eigenvalues in increasing order, and all the others are strictly greater than 0. So, so you can rewrite the graph Laplacian if you diagonalize it and write in the eigenbasis. Then it's nothing but these are the eigenvectors of the Laplacian. Is just the expression of it in the eigenbasis. I wanna say something more.
Lambda 2 is lambda I.
Yes. So let's see though exactly what's the connection with B, because that matrix is going to be very interesting for us. So
U1 is just a constant function.
is all one?
U1 is all
Yes.
one.
Okay. So in fact, if you look, if you want to determine what's the kernel of the Laplacian, which is exactly for a connected graph the all ones, the constant, and this part of the constant vector, then it's easy to see that the kernel of B is exactly equals the kernel of the Laplacian, right? So it's the same thing. Okay. So now I wanna show how else can you see the image of B. So let's see what is the image of B in, if you look at it from a different point of view. Okay, so say your graph is this now. I mean, it doesn't really matter with these edges. And consider all the functions from edges to the real numbers. And among those functions, take the subspace, take the, let pi be the projection onto the subspace that is specified as follows. So I determine a value for its vertex, and a function in the image of pi would just be determined by the difference of the values I've determined for the node. So it's going to be for this, the projection onto that subspace. I just gave it a name. Of the functions that are determined as follows. So from all the functions. No, I'm taking a subspace of the space of functions on the edges, which is determined as follows. I pick a value for its node, and the functions are the ones that are just the differences. For its edge are the differences between the, the two nodes.
So this is just the image of.
And I say pi is the projection of the subspace. Yeah, that's the image of pi, basically. That's what I'm trying to say. I'll get there. But for now, I call that pi, okay. Which is the image. I mean, it's the same image, but I wanted to. If that's clear, I shouldn't show it. I mean, I was gonna.
I'd like to find out if it's clear.
Okay, I was gonna get to that exactly, but I just wanna determine that. So f an image of pi. If f. So I defined pi. I didn't say what it is yet. I'm gonna formally define it. But before I formally define it, I wanna go to this definition, and probably all of you know what's the pseudo inverse of a matrix. But just to define it and be clear, a pseudo inverse of a matrix of the Laplacian of a connected graph, say, for example, is just what could be the inverse in the non-kernel. I mean the perpendicular to the kernel. So that's the pseudo inverse of the Laplacian of a connected graph. And note that these things are the identity on n-1 dimensions. So that's
Normally it's an n by n or n minus 1 by n minus 1.
It's an n by n matrix with rank n minus 1.
1.
I mean, this vector. I mean, it could be seen as
No, but you write it.
these vectors are n by n. I mean, it's our n-dimensional vector. So this is n by n rank 1 matrices.
So you write the product to be the identity on n minus 1. So what
The projection.
N by n matrix with the diagonal full of ones except the last one.
Yes, but I mean, in general, I would think of an n by n matrix of rank n minus 1. In my mind, I have it as acting on only this space. So it's just the identity on this space. I mean, just to avoid writing P projection of something.
It's not exactly it's not the diagonal. It's the identity on the space of U2 spanned by U2.
Yes,
U
exactly.
Yeah, you just look at the orthogonal complement to the all ones vector.
Right.
And that's your space.
Yeah, and I mean, pi is also going to have similar properties, a projection matrix and everything, which I'm going to define right now. So formally, pi is defined like that. And so now, why are those two things the same? That's what I wanted to get there. And that's going to show that pi is a projection onto the image of B, an n minus 1 rank matrix, and the images are the same. So if I formally define pi, so I claim pi is projection of rank n minus 1, so it has n minus 1 eigenvalues equal to 1, and m minus n plus 1 equal to 0. I mean, pi is an m by n matrix, right? It's indexed by edges of my graph. And 2, image of pi is image of B, which is what Avi said before. So these are the two things I want to show. So let's the first thing, well, we need to show is that this is true. And if you just write down, I mean, these proofs are almost trivial, so I don't know if you want me to do them or not. Should I?
Well, you don't have to unless somebody else.
I mean, you just
So what do you want to show that pi?
I want to show that pi is a projection on the image of B. So basically, you can go back and forth between the two interchangeably for the purpose of what I'm going to say next.
I mean, it's just 2 lines, so why not just...
Yeah, okay, so what is pi? Pi but this was the Laplacian, and this is the identity on the perpendicular to the L1's vector, so you can rewrite that as pi. So we're done. And for 2, well, the one inclusion is trivial by the definition because this is B something. So image of pi is subset. And then for the other inclusion, if you take y in the image of B, then you can write y as B some x, that x is not in the kernel. So, and all I'm going to show is that pi y equals y. So pi y is B Laplacian B transpose. So again, this is the identity, so it's bx equals y. So we're done. Pi and B are, same image. Okay, so we have now this dual view of the Laplacian of the, pi is called the projection into the cut space. The image of pi is called the cut space of the graph. I'm not sure why exactly, if you know why, but that's how it's defined. And if we view this dual image, and let's go back to the sparsifiers. So first, let's see, take an edge of the graph. I'm going to define a m by m matrix of, say, my G bar graph, that it's a diagonal matrix. So say that was an edge of my sparsifier, G bar, that had a weight now, because before we had 0, 1 weights in the graph. So I'm going to define a diagonal matrix, which is just the weight of this edge in the diagonal. And it's very easy to see that I can express the Laplacian of G tilde, as just this product.
Wait, you're assuming you have a hypothetical sparsifier?
I have any subgraph with different weights possibly. So G bar is G tilde is a subgraph of G. Maybe it has different weights, but even if it doesn't, it means the same idea. And I'm saying that for every such subgraph, you can just express its Laplacian using this diagonal matrix. I mean, it's easy to see if that was 0, 1, so it was a direct subgraph, then this would just delete all the connections that don't exist, and that could be exactly the Laplacian of a subgraph.
You could say even before, even if it was G with weight,
Yeah.
Laplacian.
But that was, but I mean, that was a W I was trying to put in there, but now I'm trying to show how to, get from Laplacians to pi, basically. That's why I'm using this notation. So, okay, so now if G tilde were to be a sparsifier, remember that we wanted that these are close to each other. So, and you can see, you can rewrite that by putting this here. But if you, again, by using this matrix, if you go to the pi world, then if I define, okay, so sorry, I forgot to, I didn't forget really to say, but I'm going to use one extra notation here, which if I consider small pi sub b to be rows or columns of pi, just say rows of pi, then by what I said before, if I restrict to the image of pi, then summation of all edges of this is the identity on that subspace.
So
I'm just rewriting pi as.
So pi is E by V matrix, the way you wrote it.
Pi is m by m.
Is m by m by m.
And this is just, this is pi in that, restricted subspace. So these are the images of the rows of pi on the, the image of pi. So this is the identity on that image of pi. I just rewrote.
So why is this? No,
by definition.
So what is the definition of pi then?
It's a row of pi.
It's the row of pi. So when you
So it's a projection.
But it's a projection of the row pi on the image of pi. So that's by definition. Okay, so, and in fact, if I, if in general I take the, so now remember that G tilde is a subgraph of G. So I can define, this weird thing that is just summation of the edges in G tilde, of the weight of the edges. So that could be the part that corresponds to G tilde. And, that is just, if I use the diagonal matrix, that is just the same thing. And note that now the sparsification requirement comes down to saying that pi G tilde.
So maybe it's better to write W tilde E because it's the weights in G tilde, right? It's not the weights in G.
Well, but G we had one weight, we had no weights, just for simplicity. That's why I wanted to avoid all this. Yeah. So now the sparsification requirement is just that pi of G tilde should be close to identity on that subspace, right? That's, I haven't done much right now. I just used the definitions and said, instead of showing that these quadratic forms are close to each other, I can show that pi G tilde is close to identity and I will have a sparsifier. But if you don't believe me yet, let's prove the following claim. So the following claim says that I don't know how, is it okay if I use the approximate notation or you want me to go with 1 plus minus epsilon? Or
but it
doesn't
depends why
matter.
we want to know precise statements of the
Okay.
theorem. So if you're going to use this,
You can use approximate notation with a constant C, and then we'll probably get.
So say if lambda min of pi G tilde is greater than 1 minus epsilon, and lambda max of pi G tilde is less than 1 plus epsilon, then actually G tilde is a sparsifier of G with the same.
it's if and only. No?
It's an identity.
Yeah, and these are the main is except for the zeros. The eigenvalue. It's a big matrix, but it has only n minus 1 non-zero eigenvalue.
Yes, but if I didn't use the ratio notation, then the one vector is the eigenvector of both, so it would be trivially true for the zero eigenvector. So if I move that here,
Pi is an m by m matrix.
yes. M by M.
It's the
Edges
size of
by
the
edges, yes.
by edges, whereas the Laplacian is
Yes,
n
yes,
by
yes.
n.
Laplacian is
So
n
the
by n.
pi has many more zero eigenvalues.
Yeah, it has n minus 1 once and m minus n plus
So
1.
lambda mean,
So when you
what
say
you really
lambda
mean is
In the project, because I use this as to be the projections on the thing. And
so you
so pi is the projection of the edge of pi on the image of pi. So it depends on how you see it. I mean,
so you
that's-
look just at the subspace.
I just
which
look
has
at the
positive
subspace.
eigenvalue.
That's why I defined it like that to begin with, because I wanted to. But for now, I'm only going to care about this image of pi, so you shouldn't worry about the non-zero, the zero eigenvalues. Is it clear what I'm trying to show? Okay, so let's solve it.
So you didn't have to put 1 minus epsilon 1 plus epsilon. You could have put any constants below.
Yeah, but because, we... Yeah, I don't know. So what that says is that that this ratio is between 1 minus epsilon and 1 plus epsilon. Okay, so, but in fact, as we noted there, pi g tilde is just this, if I use this diagonal matrix, I can rewrite it like the product of these three matrices. And note that now for y is in the image of pi. And pi is the identity on the image of pi, so y transpose pi is just y. Oops. Sorry.
Maybe you want to write it in a different line.
Oh, okay. I was
So
trying.
you are starting from the right-hand side. You are not starting from the left.
Yeah, I'm starting from
Oh,
here.
From the left. Okay, good. Yeah.
So I'm just interactively show how this transforms to being this, basically. So, okay, but y is in the image of pi, which means that there is an x perpendicular to the kernel of b. If you remember that b and pi have the same image, says that y equals bx. And I'm done, because this implies that this implies basically exactly that the quadratic forms of the two Laplacians are the same, because if you look at there, this is nothing but the Laplacian of g tilde and Laplacian of g. So now my task basically reduces on choosing a small, well-conditioned subset of these rows of pi, such that the end matrix that I'm going to build with these weights is close to the identity on the image of pi. So the task of sparsification now is this.
Well conditioned really means this bound.
This bound, yeah. I mean, close to the identity, basically.
You might also want to mention that by Wilson's lemma, you could just sample random edges.
Yes, but I'm not doing that. I mean,
No, you are not doing it, so it's worth mentioning it. So
oh, okay.
there is something like this that says that.
Yeah, no, I mean, if you wanted to have a randomized algorithm, what you could do is you could choose edges with probabilities that are proportional to the effective resistance of the edges.
No, just here. You sample n log n random edges and you sum up, you sum over that subsample pi I, pi e, pi e transpose. Right?
Yes.
That will give you approximately it's equivalent to what you said, but you don't have to.
It's not it's equivalent in a sense, but I haven't said how to. I mean, I haven't yet said anything about how to choose this pi, so I'm not sure.
No. It's what he's asking. You're going to you reduce the problem of sparsifying to
choosing edges,
edges
the pies.
with appropriate weights. Yeah.
Yes.
Choose pies. Yeah. So
Well,
you're going to do
why
it in
using
a
pi is w's?
Small pi of v and w. So my task now, new task.
Pi of e is known,
Pi
right?
of
W
e is known.
not
Pi of e is known.
But I'm gonna choose. So
you
w could be 0. Okay, I can choose just the w's and half of them.
You need to choose w's that are sparse, like most of them.
Choose we. such that the cardinality, so the number of WE different to 0 is small. So, I mean, but I can also say choose rows with weights, or it's equivalent. So that's my new task of, oops, I would want that
That's okay.
board.
You
Did I
can
want
the
that
other
board?
one down.
Well, I could write there.
Or you can write that, yeah.
Or, no, I don't, yeah, okay. So what Moritz was saying is that a way to do that is to sample rows of pi with probabilities that are proportional to effective resistance of the edge, and then you will get the summation of W, pi I, pi E, pi E transpose, that it would be close to the identity by some central limit theorem for matrices lemma. But I'm not going to show how this.
But I'm confused. I thought Rudelson's lemma would just say if I have a bunch of vectors summing up to the identity, then I can just pick n log n of those vectors.
Yes.
And they sum up to approximately the identity.
That's what I'm.
No effective resistance, I
No
guess.
effective resistance.
Well, maybe.
But the only way to make this to be close, I mean, you need to pick the weights, right? The only way to choose the correct weights and probabilities so that the expectation of these things that you're adding is identity.
So the effective resistance is already incorporated the way you define pi and the pi e's. All that is already done. Here now you just subsample.
But you need to pick the probabilities to be.
No. Rudelson lemma would just say that if I pick n log n of these edges, you're done.
And what weight are you going to put on them?
It's determined. You sum up. Now you sum up the stuff.
No, that's not correct.
Put equal weights so that you scale them up to be they're equal weights.
Yeah. So the effective resistance is already computed in this pi, isn't it?
It's already incorporated once you take this projection.
Pi gives you tells you the effective resistances. So if you sample from those vectors, you
Effective resistance is the so W times effective resistance is the diagonal entry in the pi matrix. But you want to have all the sum with the like the expectation of the the sum of the pi's that you're picking. You have to have it equal to the identity. So that's why I'm not understanding what you're saying. How are you?
What they're saying is just this, that if you have, doesn't matter pi, doesn't matter anything, you have just a bunch of vectors, call them V,
Mm-hmm.
so that VI transpose equals identity.
Mm-hmm.
Any number of them, doesn't matter. Sample, or but they are of dimension n, then you sample n log n of them, and you get this approximation uniformly.
Okay.
Sample uniformly. That's Rudelson's lemma. By the way, anybody knows why Rudelson, not us, by the winter? I mean, this is. Anybody knows why? What's the relationship?
With what?
I mean, Rudelson's lemma works for any convex body. So, I mean, it need not be finite set of vectors.
Yeah. So,
But as we don't know.
so do you know what actually? Well, if anybody knows, tell me later. There's a.
I think Alexandra would work as well.
Chernoff bound for matrices, which seems to me the same.
I think it would work as well.
So what is the question?
It's just a statement which is identical. You have a bunch of matrices. This is
No, your question. I mean.
no, so the question was just there's another inequality that I was asking what's the relationship between them. They seem to be giving the same bounds.
What is the other inequality?
So what is the special case of what?
This is a special case of.
Oh, this is a special case, but I'm wondering about Rudelson, whether it's
It follows from us.
so we'll check.
Rank one matrix.
Okay, so one way to do it is to pick randomly, and that's not the way you are going to do it.
Yeah. So, we're gonna erase that.
Can you pick n log in random edges?
Yeah, I'm actually confused too, but maybe we can talk about it after.
Yeah, so that we can
Because I don't think you're right.
I mean, I just was pointing out if you sum out what Avi said,
No, I think
The pi's
So-
of B's are not unit vectors.
They're not unit
they're
vectors.
not unit
They're
vectors.
not unit.
Their norm is equal to the
They-
effective
yeah,
resistance.
yeah.
That's what I'm trying to say. So you need to sample 1 over, the probability has to be 1 over effective resistance, or I mean,
Yeah, yeah.
some scaling.
So because they're not unit vectors. Okay, so that's
Okay, so I mean, that was my confusing. But yeah, okay, so great, but I'm not going to talk about that. So, okay, so now we're done with the review part. Great, in 45 minutes. So let's go to the BSS sparsification, deterministic BSS sparsification. So remember my new task now. So I'm going to only talk about pi, and when I talk about pi, I'm going to only talk about the image of pi. So, you know, let's try to avoid the confusion with the 0 eigenvalues of pi. Okay, so I'm going to try to pick these edges one by one, or this pi sub e one by one. So, and I'm going to build eventually this matrix. And in you know, so n, which is some order of n steps. And at each step, my plan is to increase one eigenvalue. So increase.
this is a review of the BSS spacifier, not subgraph spacifier.
No,
just
I'm going to try to give a proof
Right.
of that and then point out. So then, you know, I'm going to give the 2 proofs sort of at the same board interactively. But maybe I can, you know, we'll see. Anyway, so, you know, I want to increase sufficiently one eigenvalue. But at the same time, do not increase eigenvalues by much. And, you know, my end goal is that after n steps, the ratio of lambda min of pi g that I've built over lambda max would be very close to 1, so that, you know, I have what I wanted before. So that's my goal. And in order to do that, well, you know, as I said before, I'm just rewriting this. I start with the empty graph, and every time I update by a rank 1 matrix. So at s plus 1 step, this is going to be, you know, some edge that I've picked and some weight that I've picked. I call it T for now. And, you know, in order to ensure those properties, they define 2 potential functions. So the upper potential which is just the trace. Remember now I want to ensure that eigenvalues increase and do not increase by much. So the upper potential of a matrix is just the sum of this.
What is A? Is the adjacency matrix?
No, it's potential of any matrix. Upper potential definition for any matrix A, it's this. That's the definition. Well, for me, A's are going to be the matrices that I've created after each step, but
No,
it's a
M by
generic
M is
notation.
No, but M by M.
M by M. Yeah.
M by M
M by M.
matrices.
M by
but
M.
you only the
Well,
projection.
just let's look at the projection onto the n minus 1.
Right, but that's the matrices.
Yes, so, but generally, A is a variable in this definition. It's a variable matrix that, upper potential of A is just this. So it's the inverse, the trace of the inverse of U times the identity minus A, where U, I'm going to call it it's my barrier function. And, why did they define that, or they define that rather, is that if you know that if that's, bounded away by 0, then what does it mean? Say this is bounded away by 0 by any constant. Then basically it means that lambda max of A is less than U, right? Otherwise it could be, bounded away by infinity.
You will be a number.
U would be a number that I'm going to choose and increase every step. So all I'm saying is that if that was bounded, and it didn't approach infinity, then that means that the denominator doesn't approach 0, which means that lambda max is bounded. So I'm going to use that as a tool to make sure that this second requirement holds after every step. I'm going to show you how.
No, you are talking about lambda min or lambda max?
Lambda max.
Lambda max.
Lambda max.
So lambda max
Is less than u.
is less than u because if it was.
Because if it was really arbitrarily close to u, then this would be 0, and that would tend to infinity.
Like if you have something which are like more than far from you, then it's cancelled with something which is less than
I'm sorry?
If you have something which is more than you, but much bigger.
Yeah, but the thing is that these are going to start being less than u, and by continuity, they're never going to exceed u. So I mean,
We'll ensure the fact that.
Yeah, you have to ensure this also.
I'm going to ensure this fact, but
So actually with the dimensions, a simple comment, you can assume that the vectors lie in n-dimensional space. So then all the confusion disappears. Because you have the remaining eigenvalues as 0, you only have these many.
but I've
non-zero
already assumed
these
that.
many eigenvectors, you can assume they lie in n dimensions. And then all these matrices are just n by n matrices.
I've already assumed that. I mean, in
No,
the
there
sense.
was this confusion about dimensions of m and you can assume all the a's are just n by n matrices.
It's what I said before, that I'm only going to care about restricting to the image of pi. It's n minus 1. Okay. And for the lower potential, it's just a trace of this inverse. And I'm using that to ensure that lambda min is bounded away from L. So if
So you always assume that you keep the invariant that u is always above the lambda max, right?
yeah. And also, I need to use a lower potential to ensure that property. So, if that was, again, close to 0, then it would tend to infinity, and, this would not be bounded away. Okay, so...
You can assume they are even n minus 1 dimensional. They are of the right dimension.
Yeah, they're of the right dimension. I'm not sure why this was such a confusion, because I was trying to say that PEs are already the projections onto the image and everything.
There's some confusion.
But
So
yeah,
it's
so I'm sorry that I didn't. I don't know how to make it clearer.
Well, you can say that you pick a basis for the projection, for the projected space. It's n minus 1 dimensional, that we know. We pick a basis for it. And in this basis, we write all the pi sub x. So all of them are n minus 1 dimensional
Yeah.
vectors. We have the formal identity, some pi transpose is I of dimension n minus 1.
Yeah.
And now we are picking from them one by one.
Fine. Yeah. Okay. So there.
If you write on this, you cannot move it later. You have to
Let's
decide
see.
what you want to keep.
I'm not sure.
But if you're writing the other one, why don't pull it down and
There's another one, right? There's
Right. So I guess we're not needing these things anymore.
yeah, if you're writing it, that's probably you're not using it. Good exercise.
Yeah, these boards are made for stronger people. Okay, so we have upper potential, lower potential, and we want to ensure at every step that these two are bounded, and at the same time increase this u's by some delta u and this L by some delta L, so that lambda min and lambda max, their bounds increase by this quantity. So lambda max would be not increased by 2 mats, and lambda min would increase by enough. So that's my goal, and after n steps, I just want to say that the ratio is close to 1. And then I would be done. So I'm going to try to see how to ensure this property for the potential function, for the upper potential and lambda max, and then lower potential is going to be similar, so I'm just going to do one. So upper potential. Okay, so let's look at after one step, when I add this rank 1 operator, how would I be able to ensure that after one step, u goes to u plus delta u, and a, was a plus this rank 1 operator. And I want to ensure that at u plus delta u, I'm also bounded. So that's the invariant I'm going to try to preserve. Okay, so if you see that as a function on an n square dimensional vector, the entries of A, and you take the first order approximation, then that can be rewritten as just the value at A plus the gradient. So this is the gradient, which I'm going to say what it is. I mean, that's a general, it's not a very precise statement, but I can see that roughly what I need in order for this to be less than the previous value is that the gradient, just by rearranging that this should be less than 1. So I would just rearrange terms and said what needs to happen for this inequality to hold. Okay, so now let's be formal and see what are we going to show. So I define now this gradient term to be so I define this. I'm gonna.
So what is
No, I'm gonna.
term is u plus delta ui minus a.
Sorry, u plus delta u minus 2.
Yeah, you take minus 2. Okay.
No, I'll say where this comes from. I just wanna state the claim, and then I'll show it, and it's gonna be clear after that. So if we let this quantity be whatever it says, and lambda max of A was less than u, then if I update my barrier by delta u and my matrix by rank 1 projection, rank 1 operator, then this inequality holds, and the new lambda max is bounded. So that's the claim I want to show.
So can we read the claim? Just so UA is defined to be
This thing, yeah, which it's going to be clear why from the proof.
Okay, so it's defined, and then if we have a bound on the
Previously lambda max,
by
then we get what we want. So then potential function, new potential function is bounded, and lambda max is bounded.
well, for some delta u, which is much
For some delta u,
specify.
t is a variant too, so it's going to be a trade-off.
Yeah.
Oh, I'm sorry, I didn't. Okay. Sorry, that's what I forgot.
So actually, right away, it's not obvious that you're keeping lambda a within the. I mean, your potential might still be smaller, even though there is a lambda. The highest eigenvalue crosses the barrier. It might still be smaller. So right away, it's not clear.
Yeah, but I mean, it's not going to because of continuity, right, in the t. So like I have this trade-off there. So yeah, I mean, that's the condition I need to hold. Sorry, I forgot to write.
What's the condition you need to hold?
that, this is a matrix Frobenius product with this rank 1 update.
That's what do you mean Frobenius? It's just the inner
Well,
product
remember
of
how
matrices.
I was trying to find the gradient, like the bounded gradient, so that this holds? Then, basically I'm saying how exactly can you reformulate this condition, and that's how you reformulate it.
So this is an inner product of matrices.
Of matrices, yes. Okay, but now I need this. Do we not need that anymore? We're good if I erase that.
What, the pi L?
No, the first matrix, like if the first board. If I erase the top board.
You can use the other one for, if you.
Yeah. Okay, so let's prove that. So what the proof uses is basically the Sherman-Morrison formula to calculate what's the effect of a rank 1 update on the inverse of a matrix, because I'm using inverses. So by Sherman-Morrison, what it says is that if I have a matrix A non-singular and I update it with a rank 1 operator, and I take the inverse, then this is basically, A inverse plus an error term. So again, this big dot is the Frobenius, the matrix inner product. So my error term, if I try to calculate the inverse of a rank 1 update of my matrix, is given by this.
So what is written there? So it's T
A inverse pi transpose, which is the rank 1 matrix. A inverse.
inverse again, and at the bottom we have.
That's an inner. I can rewrite that as
Just want to make sure.
T inner product. This is just the inner product with P. It's because it's a rank 1, and if you take the matrix product, then that's what it is. So yeah, so that's what the Sherman-Morrison
The inner product with A inverse.
with A inverse.
So what do we do in the beginning where A has mostly 0 eigenvalues? When we again look at the inverse, the pseudo inverse?
No, but you have these identities, right? So at the beginning you have UI minus A.
Or you can take a tree anyway. You can start by taking just the inner.
No, but the thing is my A. Okay, so maybe it's a confusion of notation. Let's.
What you do is you have a shift by this U, and like in the beginning perspective, U is negative, and this shift ensures that you have a positive inverse.
No, I think Avi's question is what about the inverse?
No, but we don't have I have a different A here.
You start with U, but you shift.
So my A is U plus, it's the identity times something minus A, which is always.
Okay, so you start by shifting.
So I start with so for the upper potential I start with some N, say, like my U is, any value. So it's always, that's always taken care of.
All the eigenvalues are positive in the beginning.
Yeah,
but
so
tiny.
so the point is to show that they don't increase by much. And the lower potential, I would start with something negative there because I have 0 minus negative, which is going to be large. And then I do still have that property and make sure that they increase. So. And at some point, this negative becomes positive, but at this point already, lambda min is, bigger than that. So, but, let's focus on the upper potential. So, yeah, sorry about the same notation here. My B now is U plus delta U I minus A. So I'm going to use, okay, so here also. So by using this formula, I can express okay, just for simplicity, by pi E, I'm going to use pi, and by U plus delta U, I can call it U prime, just because I'm going to write it a lot. So if I write the definition of what the upper potential was, if you remember, that's just the trace of this thing inverse. So which if I use the Sermon-Morrison formula with this B, so that becomes a plus because I had minus 18 transpose. I guess I use U plus delta U anyway. I'm just rewriting what's going on there. So I just,
So minus at the bottom or
yeah, because I had minus t, say, I mean, so my t there is minus t.
I have a question about this Sherman-Morrison formula.
Mhm.
It's an identity.
Yes. It's an identity.
It's an identity with the same t and the same pi is an arbitrary vector or whatever you call it, right?
Yeah, so if you multiply this by b plus t, so if you multiply both sides, you're going to see that this is the identity. And in fact, it holds for pseudo-inverse 2 if you restrict that in the images. So, I mean, and that's what we're using in the subgraph thing. But, I mean, that needs some proof. But this is a well-known identity. Okay, so I rewrote this now, and that's what we get. So, well, trace is linear, so I'm just going to, take trace of both terms. And if you remember what that was, it's just, by definition, the potential of A, which is the first term in the first order approximation, so I'm good now. And then if we take the trace of that, you can either see it as a matrix inner product or as a trace, but it ends up being just, the inner product of this thing. I don't have enough space, I feel. Sorry.
It's a time-space trade-off.
Yeah. I basically rewrote what the trace is. And I mean, I'm not going to say anything else, just that rearranging gives me this condition. You can believe that. I mean, I don't want to write 3 more lines that have no meaning. But just by rearranging, we see that if that times this quantity, so if that inner product is less than 1 over t, then we get that this is less than the previous potential, so very good. And the statement for eigenvalues follows that by the fact that this is a continuous function of t, so eigenvalues never cross, or never cross 0. So the claim is proved. And similarly, I mean, I'm not going to show about the lower potential, but similar arguments and similar definitions of, L sub, so, you define this lower, gradient of the potential, and you want to have a condition that says this is greater than 1 over t. And similarly, the lower potential would be bounded if this is true. So, okay, but that's great. We can always find t and edges that either this or that are greater than 1 over t or less than 1 over t. So I haven't said much. But the thing is that we need the exact same edge to keep lower and upper potentials to be the same, to be bounded. So in fact, what we need is that for the same edge, this holds.
So somewhere you have to use the fact that the sum of the...
Yes. I'm going to show that too. But I mean, I haven't said, I don't want to get into what this is because it's almost identical with some minor changes. But the challenge is to find one edge that gives the 2 conditions to be the same. And the way to find it is that Well, we cannot say anything about the single edge, but we can say something about their sum. So, the thing that, they show is that if you sum over all edges, this is going to be bounded by these barriers and shifts that you've picked. And then we're going to determine what's the correct choice. And this is going to be greater than. So as long as you can pick constants that, this is less than or equal to that, then you can say that there is one single edge and a weight, t, that can satisfy the condition. So
what are the constants there? So 1 by delta u is the increment where you're looking at.
Delta u is how much I shift my upper potential. Delta L is how much I shift my lower barrier.
What about the epsilon u?
Is the bounds on these things, like how bounded is the upper potential function and how bounded is the lower potential function. But I'm going to pick all those things. I mean, I'm not going to show you how to pick those things, but you can optimize constants and pick things. So did you want to see a proof of that, or I could either give it or not?
The proof is just that the sum of these
Basically.
Well, why not? Do one.
Okay, so if we sum, maybe I can write it there because I have the definition. No. Okay, so if we sum this inner product, should I rewrite it there? Yes, I should rewrite it there. So just by writing out the sum, and this is matrix inner product again. So we knew that this was the identity. So we only get the trace of that matrix and that matrix, but the trace of that matrix.
This is the potential of the.
Hold on. Yes. Okay. So the trace of that matrix is the potential in A. And the trace of that matrix, okay, I can write it. And I'm rewriting this with their definition, which is going to be just so that's bounded by that's equal to this, and that's equal to that. Well, I mean, it's easy to see that this is 1 over delta, less than or equal to 1 over delta u, because you have this extra term here in the square. So this is less than or equal to 1 over delta u. And, this is less than or equal to fu of A, which is less than or equal to epsilon u. So, yeah, it's basically just that one step of importance that, this sum to identity. And that concludes basically the proof of the sparsification, because then every step I can do this. And if I pick some order of n steps, then the lambda min and lambda max, the correct choice of, say I move by 1 every time, and I scale, I've scaled everything by n, say now. Then I have that these two quantities are close to each other, lambda min and lambda max.
Is there a way to, it's sort of magic. So is there a high-level way to see that you can get the L and the U to approach each other? Is there, basically they are starting far apart, and you are increasing, the delta L is always bigger, so it gets closer to the eventual L and the eventual U get together. Is there any high-level way to see that they'll eventually meet?
No, they're initially, they could be together, but at the beginning, right? Because initially.
No, one
Well, initially one is minus n and the other is n.
Yeah, one is minus n. Yeah, you have.
You have something like a center limit here. So in the beginning you have some distribution, like these are like the cutoffs at the tails, and then you start adding
It's not that simple, though,
Okay,
right?
it's not
Because
that
you have to
simple,
preserve
yeah.
all the eigenvalues. I mean, if you have accumulation of eigenvalues, you need to make sure that. I mean, I haven't found a very intuitive way to see the potential function, and I don't think Dan Spillman has either, as I've talked to him. He also says it's math.
Clear that you don't even need the distribution grids. We know that if you took all of them with weight 1, you get the exact, you know this. But in this process of increasing the lower and upper potentials, why you can sort of get them? Yeah, it's not obvious.
It's not. I don't think it's obvious to anybody. In fact, I mean. But yeah, okay. So I would like to talk a little bit about subgraph sparsification now. But I've done a horrible space management job. Okay. I'm gonna move back there, I think. So that was what the sparsifier was, if we remember, reminding ourselves. And I'm not doing very good with these boards, I'm sorry. Okay, so that's the subgraph sparsification problem. So, as I said, we can't use this technique in general to get optimal results for there because, well, maybe it's an overkill. So suppose now that these two conditions hold. So after the kth eigenvalue, so we had G1 and G2. Assume that after the kth eigenvalue, pi of G1 is a somewhat good approximation of the identity. So if this eigenvalue is some constant, I don't know, or parameterized by lambda star.
We should think of as constant or small.
Most applications is constant. You would like to say, if this was 1, then these larger directions would be taken care of, sort of. But, in general, you can think of it some small constant. Or
K. So K, you want to say...
Oh, K.
I have to fix some K eigenvalue.
You can say root n, say. But it really depends on what you're doing. It could be constant. I have applied it with constant K, I have applied with root n K, I have applied it with... but it's a general thing. So what we would like to say, if G1 was already good in every direction except for the K first, then we would like to say, we can pick order of K edges of G2 and sparsify, right?
Depends also what G2 was, right? G2 was...
Yeah. Just I'm trying to say what doesn't work. So we would like to say something like that because intuitively, it would be, not very smart of us to not use the power of G1. But, this, of course, cannot be true because if you have an expander here as G1, and then one direction to be bad, but you have another expander to be G2 to, fill that up, then, this is constant. K is constant, but you cannot pick constant number of edges to make this into an expander. So, for example, that's not going to work. But at the same time, if there is no direction that G2 is really, contributing a lot, so if the trace of pi of G2 is somewhat bounded, then we can pick order of K edges of G2. Say this is the G2 bar, such that indeed we got what we wanted in the subgraph sparsification. For some constants C1 and C2. So if G1 and G2 have this relative spectrum, then I can pick order of K edges of G2 and have a sparsifier with guarantee that depends on n over T lambda star, and you know this is constant.
I'm sorry, I'm so confused. So what's the first condition saying? It's saying that
That all eigenvalues but the first k of pi sub g1, which is the summation of pi e and edges in g1, are bigger than something. You can think of it as some constant close to 1 or whatever.
do you really need the first one even if you're given the second one?
I mean, you can, if you want to, you know, that is trivially k equals t. So you can take k equals t if you wanted, if that's what you mean. But then that's stronger because it gives you way, you know, if k was less than t, but at the same, so that example with the expander, k equals 1, t equals n. I mean, that's bad, but.
Okay. So because I'm thinking of the second condition as saying that the set of edges in the second graph have a low effective
Yes,
resistance
this is
with
enough,
respect
and
to-
you could get the same with k equals t, if that's what you're saying. But then I want to be a little more technical or precise and say that in applications that for some reason these two things are far apart from each other, I can still do something meaningful. But yeah, if it's easier for you to think of it like that.
I'm just trying to see that the inequalities go the right way. So you have an upper bound. T is an upper bound on this trace. You want to say that G does not contribute a lot.
Yes, so I mean, this is the trace of this thing, right?
Yeah. Okay, so if it's small, then you get a factor n.
N is order of k, so you can think of it as k.
Okay. Now I'm fine. N is order of k.
And so that says no more than k eigenvalues are bad, and G2 is small contribution, sort of. And then we can do that. So, okay. So that's a statement. I mean, I haven't said anything
But
about it.
if the upper bound is bigger, I see then you get the worst.
Well, you get the minimum of 1 comma n over k, but it's never big. I mean, it can be bigger because trivially, as I said as an answer to this, you can take k equals t. Okay, so let's go there. So again, we're gonna go in steps and build our matrix. I mean, we're gonna follow closely this approach. So we're gonna go in steps and build, pick edges out of G2 same way with picking the columns of the pi matrix out of the edges of G2, and define potential functions, lower and upper potential, that make sure that minimum and maximum eigenvalues are what they need to be, are bounded. So the problem is that we can't keep an eye on all eigenvalues anymore because we need to pick k edges. I mean, k could be constant or whatever small thing you want. So there is no way this is going to work. So instead, what did I erase that? Okay, so instead, we have some discrepancy between the two definitions now. We basically pick edges out of G2, but focus our attention to two different matrices. So here we start with pi of G1, which is our A0. And, updated by a rank 1 update every time. And at n steps, we have pi of G1 plus G2 tilde. And here we start by the empty, which is B0, and update it every time. So at the nth step, we have pi G2 tilde. So the only reason we do that is to get the bounds. It's a technical part, so it doesn't really matter for what I'm going to say. But but note that we always pick edges out of G2 and just increment different matrices. Okay, so the best we can do now is to restrict our attention to the k smallest and t largest eigenvalues. So let S be the projection onto the k smallest eigenspace of pi of G1. And note that S is fixed throughout. And let this be the projection. Okay, let me erase that. onto T largest eigenspace of A. So we have two subspaces now that we look at. The one is fixed. It's the eigenspace of the k smallest eigenvalues of pi of G1. And the other one is variant. So every time we update A, it becomes the T largest eigenspace of this new A. So, and I mean, we need this discrepancy strongly. So, so now we define potential functions again. For the lower potential of B, is just the trace So it's just a trace of the pseudo-inverse. Okay, so this is the projection. Pi s is the projection onto the subspace. And then PS, sorry. I confuse Greek and English letters sometimes. So PS is the projection onto the k smallest eigenvalue. So the lower potential is defined as the trace of the pseudo-inverse, because we need to restrict the subspace. And it's basically, you know, the k first eigenvalues of this matrix. So it projects everything onto there, fixed subspace throughout. And for the upper potential, that's a little easier, because this subspace is always an eigenspace of what we have. So say it's, you know, the inverse of the projection. So it's just the T largest eigenvalues of A. Because this is an eigenspace of A, so always, so it always changes. Okay, so you know that's what we use. And we can have the same in invariant. We need to increase eigenvalues of this matrix now here, which is not the same as increasing eigenvalues in the whole space. And you know, this is the same, because if we bound the T largest eigenvalues, we bound lambda max. So we need to make sure that both these quantities are smaller and bounded again, and increase the u and L's by delta u and delta L every step, so that these invariants are preserved. And
sorry, just to be clear, so your t need not be an integer, but you take anything larger than t, right?
yes.
And
Okay. We're again going to try to do something very similar to previously, but let's see first what, if we were able to do that at every step, what we would get. We would get at the end that lambda max so this is bounded by something. And now we would get that lambda mean of this thing in S, restricted to S, is greater than something. These two conditions together with the bound on the perpendicular to S subspace imply, I'm not going to show that proof because it's a little too technical, but I just want to point out that these two conditions together with a lambda star bound there imply that you can get the bound on lambda mean in the whole subspace. Just have to use triangle inequality for norms, and it's not. But for now I'm going to focus on just showing this in restricted subspace and the lambda max for everything. And in fact, I'm again going to only talk about the upper potential and point out where we get the differences and what's the technical difficulties that arise from the other proof. So again, our goal is to bound at u plus delta u after rank 1 projection update, we want to have the upper potential remain bounded by the previous value. And we're gonna get we're gonna get a condition that looks very much like that. So I'm not sure if I.
So which one are you doing? First of all, in derive, so you said you need to first of all prove these two inequalities and then derive from them this condition, where the non-trivial part, I guess, is the lower bound, right? Because you are moving on the lambda mean, right? The lower bound over there.
Yes.
Yeah.
I mean,
But
from these
anyway,
two.
you are going to just prove these two, and it's going to be similar to the previous proof.
Similar, I mean, I would rather not show the proof. I just want to say that, if we use the same definition with projections, then we need to use some sort of majorization to say that in the projected space, the trace is less than the trace what would be if it was an eigenspace. And then in the summation, in the proof that we summed over everything and had here the identity, so this was a trace, we sum over everything, but here we have something with trace less than t, so we use von Neumann's trace inequality, for example, and say that this inner product is less than the sum of the t largest eigenvalues. So, I mean, basically, every eigenvalue of the new sum is less than 1. But now it's also the total trace equals t. So at most, this inner product can be the sum of the t largest eigenvalues of. Right? So basically, these are the main differences that we use.
So when you are when you are summing up over all the only of the
Edges of G2.
Yeah. So I'm just trying to figure out which is the hardest case. Where you have two of them, right? Before when you showed they were essentially the same, the lower and upper. They both summed over the whole thing. When you do it now,
Well, it's an observation, yeah. This observation that we have to use this bounds of trace and this majorization, lemma. In order, so I think the upper bound here is the hardest case.
The upper bound when you
The upper potential.
The low potential, because it's a fixed subspace.
It's a fixed subspace, so it's the same. It's just the identity on that fixed subspace. So the upper potential, you need to use that the trace is less than t, so that it's the sum of the t largest eigenvalues. And we need, basically, to figure out that we need this discrepancy in the definitions. It's also non-trivial and things like that. But I don't want to get too much into the proof because it's basically similar. I would like to talk about the application on the, adding edges to graphs and stuff like that. Okay, so if you have any questions about this, ask me now because I'm going to forget about this now and talk about something else. Sorry?
The theorem that
Over there?
yeah, I can't read this actually. So maybe you just
Yeah. You want me to write it here again?
or you just say it again.
So I'm saying that if everything but the first k eigenvalues of pi of G1 are large, and the trace of pi of G2 is small, then I can get order of k edges. So that, I pick edges out of G2 and have a G2 tilde sparsifier, so that G1 plus G2 tilde is a good sparsifier of G1 plus G2, but the good depends on these parameters that I've defined there.
Just a question would be, so when you say pi of G1, the definition of pi involves a Laplacian. Are you using the Laplacian for G1 plus G2 there, or just the Laplacian for G1?
Pi of G1 it's using the Laplacian of G1 plus G2, and it's the summation of these projections of the rows of this pi. It's the relative pi, yeah.
So you just take the sum
Over
the
edges of
Everything
G2.
makes sense in the whole graph.
Yeah.
You get the vectors and you
Otherwise, it doesn't make sense. I would just sparsify
just
G2,
finish.
right? Okay, so let's go to point 4 now. It's making graphs expanding. Okay, so the general problem is to maximize the algebraic connectivity of a graph. So I'm giving a graph G and a parameter K, and I'm asked to add k edges to G, say this k edges equals W star, so that lambda 2 of Laplacian of G plus W star is opt, is maximized among all combinatorial solutions. So, I have my graph here, say that's my graph, G. If I wanted to maximize its algebraic connectivity, I would, add edges here, so that lambda 2 of the end graph would be as big as possible. And, this is an NP-hard problem in general. And before that work, no approximation current algorithm was known. So there was just heuristics, nothing was known. No, if k is constant, there is a polynomial algorithm, right? Choose try everything. Or if k is n, this. Yeah. So, k is root n, say. That's the interesting case. Okay, so a particular instance of that problem is if G could be made into an expander graph. So say G is bounded degree for now, and I'm only going to look about solutions with bounded degree too. If G could be made to an expander graph, then that would mean that lambda k of the Laplacian of G is constant because of the interrelation of eigenvalues. So it would be greater than lambda 2 of Laplacian of G plus W star. And it will be some constant. So in that particular case, can we find order of k edges let's call that WK, to add to G, so that to make this graph expander. So that's the question I'm going to try to present.
So what is the condition on the trace of the complement of the graph then?
Trace of the...
So you had two
trace of pi.
The first one is satisfied by what you said. So assuming the graph can be made an expander, we have the lower bound of lambda stars.
Oh, I'm going to prove that.
Yeah, no, I understand. I'm asking what does the second say, the second condition say?
For this particular case, I was going to show.
Good.
Yeah. Oh, you mean for the combinatorial solution?
I'm just here G2 is the complement of G1, right?
Let me say what I have to say. If you still have the question.
G2 is W star, no?
No.
Is what you will find.
You don't know W star. It's going to be hard to find W star.
Right, but that's what you'll...
But we can find something else, and that's the something else I'm going to show. And I'm going to talk about the trace in a bit. So, in fact, I'm presenting a proof that it's not the optimal proof. But for the expander case, it's as good as optimal. So, you need to... For the sparsification thing, we need to define matrix sparsification and do other stuff for this proof to work. But for us now, it's whatever I said before is good. So this is an eigenvalue optimization problem. So we can write an STP relaxation of it. So we want to maximize lambda STP. And so this is, the graph that we're getting. If we restrict our attention to the perpendicular to the on-ones vector, the lambda of this new graph would be greater than, lambda STP. And then the summation of the weights now that we find is less than k. And the weights are between 0 and 1. So that's a semi-definite program that finds the fractional absolute optimal graph that maximizes algebraic connectivity. You can see that as lambda of the complete graph, a Laplacian of the complete graph.
What are the variables in this STP?
The weights.
They are numbers or they are vectors?
They are numbers.
This greater than equal to is a positive semi.
It's a positive
semi.
semi.
It's a positive semi-definiteness.
Yes. Sorry. So yeah, that's the Laplacian of the complete graph, or you can see it like that. It doesn't matter. So that STP, are we convinced that gives you the absolute optimal of maximizing algebraic connectivity? Okay.
Yes, but this will not be a sparse solution.
But that's what I'm trying to show.
I mean, you would give a sparse solution, but the STP need not give you a sparse.
Yes, yes, yes. The STP might be the complete graph scaled or an expanded graph or whatever it wants to be, as long as the weights add up to k. So it could be, it had n squared edges. It doesn't matter. And, exactly the point. There's no way to choose order of k edges out of the solution of the STP. Let's call that WSTP, the graph. There's no other way, even known way so far to choose small number of edges and do what we want to do, unless we apply the subgraph sparsification with our subgraph being WSTP, and we want to approximate the spectrum of this graph now. Okay, so, and the graph can be made to an expander for simple, that's the easiest case. Okay, so, let's see now what we do. Well, we just use that theorem over there. So for the first condition, we have lambda k plus 1 of pi of g. So now my g1 is g, and my g2 is WSTP.
So you actually solve the STP and then you sparsify?
Mm-hmm.
Yeah.
Okay.
So I solve the STP and get the WSTP, and then I'm trying to sparsify. So for the first condition, what this is, basically, this is the k plus 1 eigenvalue of g and the pseudo inverse of g plus WSTP by the definition of pi. And then this is greater than or equal by the min-max characterization of eigenvalues. It's the max overall subspaces of codimension k of the min, or k plus 1, of the min or x's in that subspace. So let's take as a subspace of codimension k minus 1, k plus 1 to be the one perpendicular to the k bad first eigenvectors of pi of g. So in that subspace, the min of x transpose Laplacian of gx and x transpose Laplacian of g plus STP is greater than lambda k, or k plus 1 of Laplacian of g, and then we had bounded degree, so it's some order. Okay, so, but the graph could be made to an expander, as we said before, so this is just theta of 1. Okay, so for the second condition, so for the second condition, let's see what's the trace of WSTP. Again, this is the trace, STP. So let's pick an orthonormal basis and rewrite so let's pick xi to be an orthonormal basis and rewrite the trace as summation of I xi transpose. Okay, but now this can be made into an expander. So for a stronger reason, this is greater than constant. If the optimal combinatorial solution, that's only better. So this is just less than trace. Or order of k. Because the trace is k. It's the total weight is k. But by assumption. So basically now we're done, right? Because we have what we wanted, and we can find order of k edges. These are constants now, and make the graph into an expander. my talk ends here.
And it will be like if we wanted to use the simple proof with the Buddhism, it will be k log n edges.
Yes.
No, it's not.
I mean, in that particular.
I don't even see what you would mean because it's.
But
No. You
this
can.
would be clear if you like.
You can get that with Rudolphson. The thing is, okay, here we had k and trace to be the same, but you can't get. So with Rudolphson, you can't discriminate between k and t. You can only use a trace condition. So I mean, here it's okay, but if you wanted to do something stronger, it's not okay. Okay, thanks.
Questions?
Oh.
Take your answer.
Can you, in the approximation ratio now depends on lambda k, right? So, can you get rid of that? I mean, is it possible to?
In the general case, you mean?
Yeah, no, I mean.
In the general
this,
case-
in this problem you sketched. So
No, in the general case also, if the graph cannot be made in an expander, you get a solution of value lambda squared of optimal. So it's an open question if you can get rid of that. That's what
but
you're asking.
there you don't have a counter. I mean.
We're
yeah,
working on it.
for this SCP.
I mean, we were hoping to get a constant approximation, we just couldn't.
For any lambda. For any, I mean, not dependent.
Yeah.
So you basically want to remove this lambda star in the conditions.
I mean, there you can't, but maybe you can write a smarter STP, or in that particular problem, you could make sure that k and t are the same, and lambda star is whatever. I don't know. We're trying to do that for ages, but we couldn't.